Hello, thank you for attending this talk today. My name is Dominic Messina, and I will be presenting work from myself, my colleague Henrique Oyama, and our advisor Dr. Helen Durand. The title of this talk is Tractable Control-Theoretic Constraint Design for Lyapunov-Based Economic Model Predictive Control, and in this talk I'll be going over some methods for making advanced controller design more understandable and to allow for greater confidence and safety online. And after I'll be going over some of our current work in cybersecurity detection for these types of controllers. To begin, I will first be talking about why tractable and safe control design is important. For cyber-physical systems in which a machine is interacting with its environment, safe and autonomous operation is key to achieving the best possible performance. Safe and autonomous operation requires controllers which can be designed readily to guarantee safety. However, generally, it is difficult to design controllers to meet these requirements. Issues include difficulties designing a controller which can be verified online to meet all stability conditions, and oftentimes controllers may be too computationally burdensome to implement online. To address these issues, we will be discussing modified constraint formulations and implementation strategies with the goal of allowing for a more tractable control design with guaranteed safety. Before I can discuss our modified control strategy, I will first go through a number of slides describing prior work on which our work builds. To begin, we will first be looking at a class of nonlinear systems with the following state space description. The time derivative of the state of the system is described to be a locally Lipschitz vector function of the states, inputs, and disturbances of the system. We assume the system is stabilizable in the sense that there exists a stabilizing controller h of x, which renders the origin asymptotically stable, and there exists a Lyapunov function satisfying the following condition. We define the level set omega rho to be the stability region, and it is the level set of V in which state constraints are met. Traditional economic model predictive control seeks to minimize an economic cost function with respect to a dynamic process model, a state measurement, and input and state constraints. In minimizing the cost function, the controller solves for the most optimal inputs at each sampling period over a prediction horizon, and implements the first calculated input in sample and hold for one sampling period until a new state measurement is received, and then the optimization problem is solved again. Lyapunov-based economic model predictive control builds on traditional economic model predictive control by adding two new constraints corresponding to Mode 1 and Mode 2 of operation. In Mode 1, the state is allowed to evolve dynamically within a lower level set of the stability region. State predictions made by the controller in this mode must be within the lower level set. However, with disturbances, it is possible for the state of the actual system to leave the lower level set. Despite this, the state is guaranteed to be held within the stability region if an upper bound on the disturbances is assumed. When the state is outside of the lower level set, or a time has been reached in which it is desired to return to the origin, Mode 2 is implemented. Mode 2 constrains the possible control actions to be those which decrease the Lyapunov function over a sampling period, thus bringing the state closer to the origin. If applied recursively, Mode 2 will decrease the Lyapunov function until the state converges to a small neighborhood around the steady state. So, between Mode 1 guaranteeing operation within the stability region and Mode 2 guaranteeing the state move towards the origin, it is guaranteed that the state will not leave the stability region during operation. Maintaining the closed-loop state within the larger level set known as the stability region is critical for process safety. Process safety guarantees can be verified online by checking if a number of conditions hold. However, this may be time-consuming and computationally difficult. Therefore, we consider a modified Lyapunov-based economic model predictive control strategy for potentially enhancing confidence that safety guarantees will hold without having to explicitly check. In this strategy, the process is operated in a less conservative subset of the stability region, and state measurements are collected and used more frequently than once every sampling period. When the state leaves the less conservative subset of the stability region, it is detected faster due to more frequent state measurements. The stabilizing backup controller h of x is implemented to bring the state back to the lower level set. This results in less restrictive control theoretic conditions on the stability region subset and may make closed-loop stability more likely to be maintained even if the less conservative subset is not rigorously selected. We will be taking a look at a chemical process example in which a continuous stirred tank reactor is simulated with a second-order exothermic irreversible reaction of the form A goes to B. The following state trajectories are used to describe the process model, and the control objective is to optimize process economics while preventing the closed-loop state from leaving the expected region of operation. The Lyapunov-Based controller used to stabilize the process is designed with an inlet concentration input of 0 kmols per meter cubed. The heat rate input is designed using Sontag's formula. We have a quadratic Lyapunov function of the following form. And we have a stability region of rho equals 300, where omega rho E is a subset of omega rho. And then we have the LEMPC parameters of 10 sampling periods in a prediction horizon, a sampling period of 0.01 hour, and we assume measurements are available at every 10 to the negative 4th hour. For simulations, we first operate the process under a traditional LEMPC with the lower level set rho E equals 0.98 rho, and we find that the closed loop state stays within the stability region with a profit metric of 33.05. So we decide to increase this level set rho E to 0.99 rho, and in the simulation we find that the closed loop state exits the stability region during the simulation. So when operating our modified LEMPC, we first use rho E equals 0.99 rho, and we find that the closed loop state does not leave the stability region during the simulation, and we find a similar profit metric of 33.05, which tells us that our proposed method maintains stability with similar profits for larger values of rho E, in which closed loop stability is lost under traditional LEMPC. We feel it is important to understand that the prior method does not guarantee stability for any arbitrarily selected lower level set, and that though it may be designed less conservatively, too large of a region may still result in instability. Another potential idea for attempting to make the development of constraints for LEMPC more tractable by allowing guarantees to be checked is to attempt to guess a number of terms for one of the functions such as h, and then to perform an optimization problem that selects the coefficients of that function which causes v dot to be negative throughout a region of state space. However, this concept, though initially intuitive, lacks a number of properties to make it a viable concept. Most notably, it is not guaranteed to work, or that the optimization problem used in getting h would be feasible. To see this, we know that there is no guarantee that a set of randomly selected terms to be in the function will necessarily be able to make v dot negative at each point in the stability region. Another one of the research goals which we are working on is to reduce computation time to allow for controllers to be used practically. Distributed control, in which instead of one controller controlling the whole process, a number of controllers are responsible for the respective subsystems, and they communicate their states and inputs to one another. The distributed computation in this method may decrease computation time overall. However, due to the increased networking and communication, there might be more access points for cyber attacks to target. So increasing the safety of these distributed controllers would require robust cyber attack detection and handling strategies to allow for safe and tractable control. We assume a sequential strategy in which information is passed along in controllers unidirectionally. Each controller solves for a set of inputs, assuming the input h of x for inputs later in the sequence which have not yet been solved for. And inputs from previously solved controllers are passed along to the next in sequence. Mode 1 of operation maintains the closed loop state in omega rho, and mode 2 of operation drives the closed loop state to a neighborhood around the origin. With regards to safety in the presence of cyber attacks, it is well established that cybersecurity is necessary for the proper function of critical industrial infrastructures to protect profits and safety. As engineers, we can explore cybersecurity through attack detection, inherently safer design, and safer control methods. Cyber attacks in a dynamic systems context may be able to affect a number of elements in the controller. We will be specifically looking at false state measurements, where sensor measurements are not fed back to a controller, and instead a false state measurement is provided, which may cause rogue input calculations to be applied. 3 concepts for detecting attacks have been explored within our group. The first modifies the control law at random times and enforces mode 2 of operation, in which the Lyapunov function is expected to decrease. If it does not, the process is flagged for a cyber attack. Second is a state feedback LEMPC based on state predictions. The state prediction is checked against the state measurement and is flagged for an attack if above a threshold. Lastly, an output feedback LEMPC compares state estimates with the state measurement at each sampling time and flags a cyber attack if above a threshold. The second strategy guarantees safety for one sampling period in case of an attack in which the threshold is not exceeded. However, the last strategy guarantees stability until the attack is detected if the threshold is not crossed. These detection concepts have been explored in a centralized LEMPC context in our group, in which one controller controls the entire process, and we have been working to extend these to distributed LEMPC. For example, by switching to a different LEMPC and operating under mode 2 with a distributed LEMPC, the Lyapunov function can be checked to be decreasing in each distributed controller as well as overall to flag for attacks. However, this probing-based attack detection strategy has limitations. Specifically, it would seek to switch the formulation of all distributed controllers at a sampling time to one with a new stability region to force a decrease in the randomly generated Lyapunov function over the subsequent sampling period. If the Lyapunov function does not decrease in an individual controller or overall, this can be indicative of an attack. However, even in a centralized framework, this type of strategy does not guarantee detection of a false sensor measurement cyber attack, so it does not guarantee detection for a distributed framework either. For example, our group has previously looked into this in the context of a centralized LEMPC for the CSTR discussed earlier in this talk. The CSTR was simulated for 0.1 hour of operation, initialized off steady state within the intersection of 2 stability regions with different Lyapunov functions V1 and V2 designed around different steady states. The stability region using V2 is contained within that using V1. 2 different attacks are applied, one attack with a constant false state measurement and another attack with a false state measurement that varied slightly over 9 sampling periods before remaining constant. In this case, the first attack will be detected under either Lyapunov function used for the probing starting at the initial time as a lack of decrease in the Lyapunov function value, but neither probing strategy would detect the second attack. Still, equipping a distributed controller with additional checks for cyber attacks, even if not guaranteed to detect the attack, could provide additional layers of protection. In conclusion, designing advanced controllers with safety verified can be challenging. In the first part of this talk, we discussed concepts for attempting to make it easier to accept initial controller parameters in LEMPC rather than verifying that the parameters will meet closed-loop stability conditions, but without checking the stability conditions, stability cannot be guaranteed. We also discussed concepts related to verifying that either attacks can be detected or that stability can be maintained in the presence of attacks. Methods explored for centralized LEMPC could be explored in the context of a distributed framework. A probing-based strategy could allow for detection conditions to be checked overall and with respect to individual controllers. However, the probing-based method does not guarantee attack detection. We would gratefully like to acknowledge financial support from the National Science Foundation, Air Force Office of Scientific Research, and Wayne State University.